Hi, in this video we are going to learn how to sketch the graph of a gradient function for any given function. Let's quickly recall what a gradient function is. When you have a line graph, we know that we have a constant gradient. So let's say the first one is y equals x minus 4 and the second one is y equals minus 2x plus 5, right? We know that when we have y alone, the coefficient of x is the gradient. So this one is 1, this one is negative 2. And it doesn't matter which x value we're checking, the gradient at this point is the same as the gradient at this point. The line does not change. Hence, the gradient does not change. Whereas, on a curve, the gradient changes constantly, and there is only one way to describe the gradient. We just draw tangent lines at a given x value. So, for example, this tangent line at this x value at this point has a positive gradient, whereas this tangent line at this x value at this point has a negative gradient. And we also know that the tangent lines at the stationary points are horizontal. This means that the gradients are 0. Now, just because the gradients are variable, we have this gradient function. So the derivative of a function is always the gradient function. And to find a gradient of the tangent line or the gradient of the curve at a given x value, we have to substitute that x value into the gradient function, which is the derivative of the function. Now, one other observation is that when you have the tangent lines drawn approximately on this direction, you get a positive gradient. When the tangent lines are drawn like this direction, they have a negative gradient. We know that the horizontal tangent lines have the gradient to be 0. And if you have a vertical line, then the gradient is undefined. So now let's try to figure out the behavior of the gradient function by looking at the function itself. So if we have a positive gradient, if the function is increasing like here, right, we'll have the positive gradient. We should be sketching the gradient function graph above the x-axis because that is where the y values are positive. And certainly when you have a negative gradient, the graph of the gradient function should be below the x-axis. Maximum and minimum points should cut the x-axis, whereas the point of inflection will touch the x-axis. The graph of the gradient function will cut the x-axis at the maximum and minimum of the function itself, because that's where the gradient function's y value will be 0, right? Because the gradient is 0. And for the point of inflection, it will touch the x-axis because we know that at the point of inflection, let's say this graph, right? This is the point of inflection. The gradient function will have the same values. It's positive, positive, or if it is something like this, then it is negative, negative. So the sign of the gradient does not change. That's why it touches the x-axis, but it stays in the same area above the x-axis or below, right? Now, we'll, of course, understand much better when we see an example, but these are the things that we have to consider while drawing the graph of a gradient function. 2 more points before we move on to an example. The vertical asymptotes will stay the same as vertical asymptote, whereas the horizontal asymptotes will be the x-axis in the graph of the gradient function. The reason for the horizontal asymptote becoming the x-axis is horizontal asymptote is something like y equals 5, let's say, or minus 2. So this is a constant function. So when you take the derivative of a constant function, you end up with 0, right? Or we know that the gradient of horizontal lines is 0, so we end up with the x-axis y equals 0 as the gradient of such horizontal asymptotes, right? So it must be the x-axis. Now is time for an example. So we have this cubic function graph given, and we're going to now draw the graph of the gradient function, and we must show the coordinates of the points where the graph cuts or meets the x-axis. Now let's start with the maximum and the minimum values. So we know that x equals -1 and x equals 1 have the local minimum and the local maximum. So I'm going to mark them on my graph. So it's -1 and 1, because I know the gradient function graph will cut the x-axis at these points. Now, before x equals -1, so I'm talking about this region, I know that the graph is here positive in terms of gradient, but the gradients will approach to 0 because I'm approaching to the local maximum. So this means my gradient values will be higher when I'm away from -1. So this means I'm going to start from somewhere here, and I will cut the axis at -1, because at -1 the gradient is 0, and after that the curve starts decreasing, which gives me negative gradient. Now the gradient is negative until the local minimum, right? So I don't know the values, I don't know where the turning point for this graph is, but I know that my graph will cut the x-axis again at x equals 1, because that's where we have the local minimum. And then, after the local minimum, I have the gradient to be positive, so I will just draw my graph up on the positive y-axis. So this is how I draw the graph of the derivative or the gradient function. Another example. So this is a graph of a function with a horizontal asymptote and only one local minimum. Now first, let's find out where the local minimum is in our gradient function graph. So it is -3, so it's x equals -3. So let's mark it here. This is -3, and now I know that the gradient function graph will cut the x-axis at -3. Another thing that I know is this is the horizontal asymptote here, and this is y equals -2. Now this horizontal asymptote will be the x-axis in my graph of the gradient function. So let's start working on the function graph. Now obviously the function is decreasing, and therefore the tangent lines that I draw will have negative gradient. So I'm going to be drawing my curve below the x-axis, but I know also that the gradients will be approaching to 0 because we have this local minimum at -3. So I will come from the negative values, and I will cut the axis here, and then I will start having positive values, but these positive values will start approaching to 0 because the function graph goes very close to the horizontal asymptote. So I have to draw something similar approaching to my horizontal asymptote, which is the x-axis. So my graph should somewhat look like this. So this is the gradient function graph. As we don't know the function itself, we can't find the gradient function as an algebraic expression. Therefore, we cannot work on the y-intercept, so we don't worry about that. All we think about is where the graph cuts the x-axis or whether we have a horizontal asymptote or not. And please also note that the vertical asymptotes, unlike the horizontal asymptotes, do not change at all. They just stay the same. So the key to drawing these gradient function graphs is that you have to think about the value of the gradient. It is really tricky to draw these graphs, so make sure that you always think about the gradient of the function along the curve. Thanks for watching.